For billions of years, our planet has gracefully orbited a truly magnificent star, a celestial beacon that has nurtured life as we know it. The Sun, a powerhouse of energy, a constant presence in our skies. It bathes our world in life-giving warmth and radiant light, providing the essential energy that allows life in all its diverse forms to flourish and thrive. But what truly powers the Sun? What is the secret behind its seemingly endless energy? It's not fire as we know it, the kind that dances in a campfire, but something far more powerful, a process that dwarfs any earthly combustion. Deep within its core, the heart of the solar furnace, under unimaginable pressure and searing heat, conditions that defy our everyday experience, the Sun unleashes the force of nuclear fusion. This is the very same process that powers every star we see twinkling in the night sky, a cosmic engine relentlessly forging light and heat, shaping galaxies. Fusion is the universe's ultimate and most fundamental power source, building the very elements, atom by atom, that ultimately make up our world and everything within it. Understanding fusion isn't just a scientific pursuit, it's a profound journey into the very heart of creation, a quest to understand our origins. Here on Earth, brilliant scientists are racing against time to replicate this stellar fire, hoping to design and build machines that can safely and efficiently harness fusion's immense power. If they succeed, fusion could provide a source of clean, safe, sustainable and virtually limitless energy for all of humanity, ultimately freeing us from our dependence on polluting fossil fuels. This ambitious quest is undoubtedly one of humanity's greatest scientific and engineering challenges to date. It's a compelling story of human ingenuity, unwavering perseverance, and enduring hope for a brighter and better future for generations to come. So let's embark together on an extraordinary journey, from the fiery heart of our Sun to the cutting-edge fusion labs here on Earth. We'll have the privilege of meeting the brilliant minds behind the science and explore in detail how we're learning to harness, control and utilize the very engine that powers the universe and sustains all of existence. The captivating story of nuclear fusion is, in essence, the story of our own boundless potential, and ultimately our place within the grand and awe-inspiring tapestry of the cosmos. To truly understand the immense potential of fusion energy, we must first journey into the world of the infinitesimally small, the realm of atoms. These are the fundamental building blocks of everything around us. At the very heart of every atom lies a nucleus, a dense core made up of protons and neutrons, all bound together by an incredibly powerful force known as the strong nuclear force. This force is what holds the nucleus together. Fusion, in essence, happens when two light nuclei, such as isotopes of hydrogen, are forced together with such immense energy that they overcome their natural repulsion and merge, ultimately forming a heavier nucleus. The resulting new nucleus has a fascinating property. It weighs slightly less than the combined weight of the original nuclei. The missing mass, seemingly vanished, is actually converted into a truly tremendous amount of energy, a phenomenon precisely described by Einstein's famous equation EMC2. This very process is the source of the Sun's incredible power, the energy that sustains life on Earth, and it's also the ultimate goal of fusion research efforts right here on Earth. Unlike nuclear fission, which involves splitting heavy atoms like uranium, fusion joins together light atoms, promising a much safer energy source with significantly less radioactive waste. Fusion relies on abundant and readily available fuel, hydrogen, which can be extracted from ordinary water, offering the potential for a clean, sustainable and enduring legacy of power for generations to come. Fission breaks down atomic nuclei. Fusion builds them up, releasing the very essence of starlight in the process. The ultimate dream of fusion research is to recreate the gentle yet immensely powerful sustained process that fuels the stars right here on Earth. The story of fusion is a tale of scientific discovery, built by brilliant minds over decades. In the 1920s, William Harkins and Francis Aston proposed that stars draw energy from fusing hydrogen into helium, hinting at the missing mass that becomes energy. Sir Arthur Eddington popularized the idea that fusion powers the stars, connecting atomic physics to cosmic energy. But it was Hans Baade in 1939 who detailed the nuclear reactions that power stars like our Sun, earning a Nobel Prize. This journey, from early hypotheses to Baede's blueprint, was a triumph of science, revealing the life story of the stars. These discoveries laid the groundwork for humanity's quest to build a star on Earth. Fusion research is not just about physics. It's about understanding the very engine of creation. Creating fusion on Earth means replicating the extreme conditions at a star's core. 3 challenges known as the Lawson criterion must be met: extreme temperature, high density and long confinement time. First, atomic nuclei must be heated to millions of degrees, forming a superhot plasma. Second, the plasma's particles must be packed closely enough to collide and fuse. Third, the plasma must be held in this state long enough for fusion to occur and produce more energy than it consumes. Unlike stars, we lack immense gravity, so we use powerful magnets and lasers to confine and heat the plasma. Achieving all 3 conditions at once is the heart of the fusion challenge. Stars have gravity on their side. On Earth, we rely on human ingenuity. The quest to tame a piece of the Sun is one of science's greatest engineering feats. Deep in the Sun's core, temperatures soar to 15 million degrees Celsius, driving the proton-proton chain, the main fusion process in stars like ours. 4 hydrogen nuclei fuse through a series of steps to form 1 helium nucleus, releasing energy at each stage. The process begins with 2 protons fusing, overcoming their natural repulsion to create deuterium. Deuterium fuses with another proton to form helium-3. 2 helium-3 nuclei then combine to make helium-4, releasing protons to restart the cycle. In larger, hotter stars, the CNO cycle dominates, using carbon, nitrogen and oxygen as catalysts to speed up fusion. Both processes fuse hydrogen into helium, releasing vast energy that slowly travels outward as light. This ancient energy eventually escapes the star's surface and becomes the sunlight that warms our planet. Every ray of sunlight is a gift from the Sun's fusion furnace. Fusion is the cosmic engine that sustains life on Earth. Once we understood stellar fusion, the next question was, can we do it on Earth? In 1932, Mark Oliphant achieved the first artificial fusion reaction, proving fusion was possible in the lab. The pursuit of fusion took a dark turn with the hydrogen bomb, an uncontrolled, explosive use of fusion's power. After the war, the focus shifted to peaceful, controlled fusion for energy. The Cold War kept much research secret, but in 1958, the Atoms for Peace Conference opened the door to international collaboration. Scientists began sharing breakthroughs, uniting around the challenge of bottling a star. The quest for fusion energy became a global effort, shifting from weapons to hope. The journey to control fusion, a quest driven by the promise of limitless clean energy, has spurred the creation of extraordinary machines, pushing the boundaries of engineering and physics. These devices represent decades of innovation. The tokamak, a concept pioneered in the Soviet Union, stands as a testament to international scientific collaboration. It uses incredibly powerful magnetic fields, precisely shaped and controlled, to meticulously confine plasma, the superheated state of matter where fusion occurs, within a donut-shaped chamber. The Joint European Torus, JET, a collaborative project located in the UK, has set significant records for fusion power output, firmly demonstrating the tokamak's potential as a viable path to fusion energy. In 2021, JET achieved a remarkable feat, producing 59 megajoules of sustained fusion energy, a sustained and controlled reaction, a major milestone that energized the entire field of fusion research. Another distinct approach, known as inertial confinement fusion, takes a different route. It harnesses the power of lasers, such as those at the National Ignition Facility, NIF, a leading research center located in California. These lasers are used to compress fuel pellets with incredible force, creating the conditions needed to trigger fusion. In 2021, NIF proudly announced that they had achieved ignition, successfully producing more energy from the fusion reaction than the energy delivered by the lasers themselves. The next significant leap forward is ITER, which will be the world's largest tokamak ever constructed, currently under construction in France through the collaboration of 35 nations. ITER's primary objective is to produce a substantial 500 megawatts of fusion power. while only requiring an input of 50 megawatts of power. This would represent a tenfold energy return, a significant milestone. It's important to note that ITER isn't designed to be a commercial power plant. Rather, it serves as a crucial demonstration that fusion can indeed work and be sustained at a scale relevant to future power plants. It stands as one of humanity's most ambitious and complex science projects to date, a global bet on realizing a future powered by clean and sustainable energy. Controlled fusion promises clean energy with unmatched benefits. Its fuels, deuterium from seawater and tritium from lithium, are abundant and accessible worldwide. Fusion reactors are inherently safe, no risk of meltdown, and the process stops if disrupted. The main byproduct is harmless helium, and radioactive waste decays quickly. Fusion could also help transmute long-lived nuclear waste into safer forms, cleaning up our nuclear legacy. Fusion's powerful neutron sources could create valuable isotopes for medicine and industry. Most exciting, fusion could power deep space travel, making missions to Mars and beyond much faster. Fusion propulsion could turn science fiction into reality, opening the solar system to exploration. The gifts of fusion extend far beyond electricity. They could transform our world and our reach into the cosmos. We're living in a remarkable era for fusion research. Recent breakthroughs at JET and NIF prove the science is sound. Now the challenge is engineering. Projects like ITER aim to sustain fusion for long periods and make it practical for power generation. Private companies are joining the race, bringing new ideas and accelerating progress. From advanced tokamaks to novel designs, innovation is driving fusion closer to reality. Major hurdles remain: developing materials, handling tritium, and converting fusion heat to electricity. But global teams are tackling these challenges with unprecedented collaboration. For the first time, many believe commercial fusion is possible within our lifetimes. The quest to harness the power of the stars is a testament to human curiosity and cooperation. If we succeed, we'll secure a clean, sustainable future, powered by the same fire that lights the universe.